Okay, I'll be talking more about sediments. And I already talked about things in the rocks that don't really fit long ages. And this is really a continuation, but focusing it more directly on how that relates to geological time. So, why do many scientists believe in the geologic time scale, millions of years? Why? I mean, we're showing you evidence that it can't be true. Why do they believe it? Well, radiometric dating, of course. That's the big one. And then these two together, worldview, philosophy, methodological naturalism, meaning there is no God, there's no creation, everything goes along the way it does. And naturalism requires millions of years for evolution of life. And so these two together is why they believe in that. Is there any other evidence? Well, yes, there is, but how will it be interpreted? Everybody who has a strong commitment to a worldview, your geological evidence, you put that together with your worldview to reach a conclusion. We almost never look at data just by themselves. We have some way to interpret them, to decide what they mean. And if you, in this case, for most scientists, all evidence will be interpreted by the naturalistic worldview, which is long ages. Assumptions rule. The assumption of long ages, the assumption there's no creator. That rules when you're dealing with ancient history. Okay, so in study of ancient history, the scientific process follows this sequence, and you don't usually see it described this way. You have evidence, but you don't go from there to conclusions. It's the evidence and then assumptions, usually unstated assumptions, which you don't even talk about. But the assumptions determine how you will reach a conclusion, how you will interpret your data, if you're working with a naturalistic worldview. We don't just naturally go from data to conclusions without some way that determines how we're going to interpret that data. So when we're dealing with, most of science is wonderful, it's awesome, I love it. But when we're dealing with ancient history that we can't even go back and see what happened, assumptions rule. And that may be a hard thing to accept, but that is in fact true. Assumptions rule. Is there an alternative to the long ages? Okay, let's just say if the naturalistic worldview is not assumed, if you put that aside, does the evidence really indicate long ages? That's what I'm talking about here, and Dr. Phillips has been talking about. Oops. Okay, the secular worldview. Geologic formations are formed by the same processes as today. This is a little review from yesterday. These modern processes, this mud flow a few blocks from my house, that's the way things happen today, and rivers. The biblical worldview says no, there were much more catastrophic processes that happened very rapidly, and this is really why the world is like it is. There is a real alternative. Radiometric dates, millions of years, and modern processes, but a lot of geological evidence and biological is not compatible with those millions of years. And that's what we're talking about today. So does this biblical worldview work? Yeah, we can say it's great, but does it really work when you look at the evidence? Yes, it definitely does. There is growing evidence that doesn't fit the long time scale. And of course, this evidence has been there all along, but we didn't understand it. We're understanding it more and more. So we're going to examine evidence that favors short time and catastrophe. Okay, we looked at these rocks yesterday, but we're going to focus on one other aspect of these today. These layers you see, we call beds. Geologists call them beds. And so these are bedded sedimentary rocks. They are layers. Those are just not lines on the face of the hill. Those are layers that go back into the rock for a mile, 100 miles, whatever. So bedded rocks. Why are they so bedded? I mean, it's just routinely. These rocks have very clear, distinct beds. Okay, why are there such distinct beds? And why do we ask? Why do we care? Why are those beds preserved? Okay, why do we ask those questions? Because if million years of years had passed, those distinct layers should not exist anymore. They should not exist. Okay, modern geologic processes, these rivers, streams, and flash floods, they produce very complex deposits, not evenly bedded. This is the first factor we're going to look at. If you cut into the hillside where a river is flowing, it's not making these widespread layers. It's not doing that. It's making very complex deposits as it moves from side to side, chews away at the riverbank, and deposits more sediment in complex ways. That's what a river does. It does not produce these layers. But that's only the beginning. We have these. There's sedimentary rocks are everywhere. These are limestones. These are this is a mudstone and a variety of things here. Oops. Okay. Here's another. This is a hillside in Utah, and we're there examining these rocks. We do some interesting things when you're a geologist. You see these fine layers. This whole thing is layered in very fine layers. There we have beautiful layers. I love this formation called the Somerville Formation. So beautifully layered. These are not like modern complex deposits. And furthermore, then the other reason why these beds should not be there anymore is something we call bioturbation. Bio meaning biological, turbation, something that's disturbing the sediment. Okay, if you go out on the beach and you spend time watching, you see these little creatures that dig in the sand. At least they do down where I live. They dig holes in the sand. A lot of them burrow through the sand. They're finding little food particles from the lunch that we lost, and they're eating it. But they're burrowing through the sediment all the time. This is just happening continually. And that modifies the sediment. It disturbs the sediment. It destroys any layering that's there. So you have these creatures. He's coming out of his burrow. This guy is heading toward his burrow. And so they do this. They do this so much that it churns up the sediment. It will destroy any layers that are there. Mix them all up. And they produce these burrows, which if that becomes rock, those will look like this. These are fossilized burrows of these kind of critters. And they do this all the time. Okay, the mixing of sediments by burrowing animals occurs rapidly. If millions of years had passed, the layering in these bedded rocks should be eliminated by bioturbation. It should just be gone. It's all mixed up. Just like you put things in your blender. Layers are not going to stay anymore. How about if it's not formed underwater? Well, it's pretty much the same. The terrestrial environment, there are worms, rodents, tree roots. This hillside you can see has been pretty well bioturbated. So I'm going to use bread as an analogy for layers of rock. So like I said, these lines are not just lines on the surface. You're seeing beds, layers that go back in, just like a stack of bread slices. They go back past the surface. They are slices. And so if you have a slice of bread, you put another one there. And then you leave that out. Just leave it out somewhere for I don't know how long it would take, days, weeks. It's going to look something like this. Critters find it and burrow through it, and the mold comes along. And then if you leave it there longer, some other things happen. And so this is what happens when time passes. Things get damaged. And if you they leave these two laying out, then you put a couple more on top. Now you can tell which ones were exposed out there for a long time and which ones are fresh. These haven't had the time to get all this destruction, all this bioturbation. And if you leave the whole thing out for a long time, the whole thing is churned up and messed up, and it may even destroy those layers. Okay, under the ocean here, there are a lot of things happening right there in front of you. All this bioturbation is happening. But in this sediment, all these layers, we don't have that. There's no bioturbation. Okay, why? Why did this not happen? And it's a matter of time. So as this layers get deposited, and then if you cut through that right away, you got all these layers with no bioturbation, no burrows. A little time goes by, and now you have some burrows. You can still see the layering, but there are burrows down through it. If time goes on longer, it's all going to be destroyed. This has just been thoroughly bioturbated, and there's no layers left. In the modern world, how long does it take to destroy all those layers? 10,000 years? Well, no. Oops. Takes days or weeks, maybe even hours. It depends on the situation. But this happens amazingly fast. These creatures get in there, and they're finding food, they're finding ways to live, and they just do the job really quite rapidly. And in fact, in a book that I have on this process of bioturbation, the normal expectation, what normally happens is 100% bioturbation. All the layering is destroyed. If that's not true, anything less than 100% requires an explanation. Because 100% bioturbation was what happens normally. So if that didn't happen, there has to be something that can explain why it didn't happen. And time is a very important factor, probably the most important factor. If there's a little time pass, you have a few burrows, but not enough to destroy these layers. If time goes by, this is what you end up with. So here's just a little diagram. These lines represent these layers of rock. And if you don't have much time, you don't have any bioturbation. The more time that goes by, the more bioturbation until there's nothing of those layers left. So why are all these layers here? It hasn't been bioturbated. There hasn't been enough time for that to happen. If the time had gone by, this is what it ought to look like. Nothing left, all churned up. And with that, if you destroy all the information, these layerings, geologists really can't do much to try to figure it out because it's all been destroyed like this. But it hasn't been destroyed. Whoops, I don't know what happened there. That wasn't geological time, that was something else. Okay. So the layers are still there. And that's very typical. Here's another formation, the Green River Formation. These layers, fine layers, were deposited in an ancient lake after the flood sometime, or near the end of the flood. Okay, Dr. Chadwick and I spent a couple of years doing research on this out in the field, driving our four-wheel drives out in the wilderness and finding good hillsides that we could study. Quantifying bioturbation. How much is there really? I mentioned this friend of mine who was in a class by a very prominent person who studied bioturbation, and this teacher, a world expert, she made a comment one day. She said, "I don't lose sleep over it, but I wonder why there isn't more bioturbation out there." So there isn't not enough bioturbation. So we wanted to know really how much is there. So we would go out there and we would look at a rock and examine it, and then classify it. If it had no bioturbation, or maybe just a few, but not enough to disturb the layers, it's a number 1. If there's more, then it's a number 2, number 3, number 4 is all bioturbated. So we could classify each section of rock that way. So we would go up to a formation, a geological formation, and we would do what a geologist calls measuring a section. Start from the bottom, You go up through the rock, you measure the thickness of each little layer, and you describe what it's like. So you get a description of this whole hillside. And for us, for each part of this hillside, we would classify it in these categories. How much bioturbation was there? Okay, and so this is a very quick summary of what we've done. This is the geologic column from Cambrian on up, and each of these vertical lines is a section that we measured. And so we measured something like 31 sections all the way up through here. And for each one, we would end up with a diagram like this. This is the section, this rock formation from bottom to top. And then we would look for burrows and classify it in one of these categories. This is the Triassic Moenkopi Formation. Triassic is right in there. Okay, so does it have any burrows? We would first of all make some marks here on the side. Yeah, there are some burrows. So it wasn't that we couldn't see the burrows. We can see them. We know they're there. There are some. But how much? Well, all the way through down this thing, there is only number 1. Almost no bioturbation at all. Not enough to disturb the layers. Okay, this is another one. This is quite typical of what we found. Other formation is the Cretaceous. Mancos Shale, that's Cretaceous, is right up. It's one of these right here. Okay, there are burrows at a number of levels here. So we know there are critters there. But how much bioturbation? Well, mostly it's number 1. There's a couple of spots where there's a number 3, and one area where we had number 4, this kind. So, but this is very close to the average. We very rarely found this much bioturbation. Okay, if sediments had formed over tens of thousands or millions of years, there should be mostly number 4. But that was not the case. There are some animal burrows all through the geologic column. Now, that's not surprising. In the flood, there were animals living and moving around until they finally would get killed. And so there are animals moving around trying to survive in all the chaos that's around them. But they weren't able to do very much. The rocks are mostly number 1. And I've put here, that's a conservative figure. Probably it's more like 95 or 98%. It's just number 1. Hardly any bioturbation at all. Occasionally 2 or 3. Very rare, number 4. So these critters just weren't there doing their job. Things were happening too fast. There is typically far too much preserved bedding. If there wasn't enough time for burrowing to destroy that bedding. And so this is I think a strong argument against the reality of the radiometric time scale. Okay, conclusions on bioturbation. There is some bioturbation scattered throughout the geologic column. Animals were moving around and trying to survive during the flood. There are occasions possibly where you could think of some reason why they couldn't live there and do bioturbation, but that's very minimal. Almost all the time they should have been there, but they were not. So the evidence supports our hypothesis of short time. Not enough time for these critters to do their job. Okay, there's the other one. Dr. Phillips just gave you this talk. I'm just going to give a couple of slides to summarize some things. Proteins and other biomolecules in soft tissue are destroyed when not protected by being in a living organism. This occurs within thousands of years or tens of thousands of years at most, not millions of years. So they're finding more and more of this biomaterial in ancient fossils, very old fossils. And this is a serious conflict for the conventional science. It is not compatible with the radiometric time scale. And Dr. Phillips has actually already talked about this. Well-preserved fossils. This one is one that I find very amazing and fascinating. What happens when animals and plants die? Okay, they don't just kind of lie around out there, fortunately. They decay. There's tissue destruction by vermin, scavenging, disarticulation of skeletons. This all proceeds. If you can do The study of this kind of thing we call taphonomy. You can do some taphonomy research yourself. You find a dead cat on the road, kick it in the ditch, then you go every day and you study it. What's happening? What insects are bothering it? How long does it take for the bones to come apart? That's taphonomy research. Exciting stuff. But it helps to understand fossils. Okay, you can put fossils, say, in a couple of categories. A lot of fossils are broken and battered and torn up. And that's really what we'd expect. That's the normal thing we would expect to find. But there's the other category that you're seeing here, well-preserved fossils, just amazingly well-preserved. I'm going to show you some more slides. Okay, this insect, how did he get preserved that way? Just tremendous. All these things are fly larvae. And you're not likely to expect fly larvae to lie there and be, for years, for a long time, even a few days. These are beautifully preserved fly larvae in the rock. Some more typical fossils, wonderful things. This bat, in sediment, every bone is in place. Nothing has damaged this thing. This leaf, again, the same thing. Turtle. Soft-shelled turtle, every bone in place. Nothing has disturbed that thing. This one right here is one of my favorites. Any guesses? That's a coprolite. That's a polite name for fossilized poop. Okay? This is about an inch long. It's crocodile poop, most likely. And this is not an isolated one. There are, if you go to something like the Green River Formation, there are millions of these little fish droppings that are just everywhere. And they're this thing. Okay, and you see it's in layers. The radiometric time scale for this formation would indicate that these very thin layers, were like one or a few per year. And this thing, I looked at this cross section and I counted the layers under a microscope. 180 layers it took to bury this thing. So would you buy that this lay there on the bottom of a lake for a century and look like this? Not a chance. Just not a chance at all. And a lot of these things are in that same formation, millions of fish. They're all like this. That just did not take much. That was buried very, very rapidly. But fossils, so many fossils are like that. Okay, this is what happens in nature. This cow up in Wyoming made a bad choice, tried to cross this cattle guard. When I took this picture, the insect larvae had already removed the tissue. In a year or so, this is the way it looked. So this is what happens in the modern world when something dies. It gets recycled. But what we have in the fossil record, this amazing mess of fossils, this trilobite, very fancy trilobite. And there are many kinds of these. It's just incredible. This dinosaur. When you go to a museum, you'll see skeletons like this. Some of them were found as a complete skeleton. Others were partial, and they've repaired and replaced bones. You'd have to ask them, most usually, how much it's been restored. But there are a lot of them that were complete. There's a complete Tyrannosaurus Rex in the Chicago Museum that they bought for $8 million. Quite a few years ago, and it'd be much higher than that now. Okay, here are all these fish, wonderfully preserved. 14-foot crocodile, every bone in place. A palm frond with all these fish around it. The mixture is a little odd too. A palm frond with all these fish, but they're all well preserved. This is a soft-bodied creature. In fact, it doesn't have bones. Excuse me, cartilaginous skeleton. It's all there. This guy is all there, every bone in place. And there are, I'm showing you a small sample. There's an amazing amount of fossils like this. If you'd like to get a better picture, go sometime to the Tucson, Arizona Fossil and Mineral Show. They have it every year. Dealers come from around the world to sell their fossils that they've found. And some of the hotels in town are just taken over. Every room is a different shop. You're going to wish you had a lot more money if you go there. But anyway, there are these amazing fossils. Okay, what happens today? In the African plains, there are wildebeest by the millions. I really think that's not a very balanced ecosystem. So many animals of one type in one place, they have to make annual migrations, long migrations to find food, and enough food for all those animals. They have to cross rivers. And thousands of them die in the rivers every year and are drowned. And some years, in 1 year, in fact, some years, 10,000 wildebeest drown. Okay, here's what you got then. There are going to be a lot of fossils, right? You'd think so. No, there are no fossils ending up from this. This has been studied carefully because they want to know what happens to these bones. After 10 years, no bones. In fact, most of them are gone in 7 years. The bones get chemically recycled into the ecosystem again. So it helps the ecosystem. It's kind of hard on the wildebeest. This is what happens today. In North America, there used to be millions of bison, these large cow-like animals. When the pale-face Europeans came with their guns, they're all gone except for a few in preserves. And before we got there, the native people had been killing these for centuries for food and other materials. They're rare to find any kind of bone that could be a potential fossil. They just are gone. That's what happens today. But how do we get this? Why are there so many wonderfully preserved fossils? These things are soft-bodied. These are kind of squid. These are kind of small, a few inches long, beautifully preserved. This guy's soft-bodied. That bat is incredible. A good preservation of organisms occurs in what? In catastrophic burial. You do not leave this thing lay around there and have to be preserved like this. It takes catastrophic, extremely rapid burial. And yet there are so many fossils like this. How is that? How could that be? It takes catastrophe to do it, and these modern catastrophes are not going to do it. This is not enough. You have to have a real catastrophe to bury those. I really think without Noah's flood, we would have very few fossils. The fossil record would be just very inadequate, scattered and sketchy, and not very much there. And so now if I went to a paleontology meeting and told them this, I don't know what they'd say. They'd probably just think, wow, this guy's an idiot. But no, how else are you going to get those fossils? They aren't going to happen in the world today. So I think if there had not been a catastrophic global flood, there would be only a very meager fossil record, if any at all. There's one other interesting thing here. The geologic column, this has been studied, where you find different kinds of fossils. The Pleistocene is the upper part of the geological record. It's really kind of bringing us to the modern world. The conditions in the Pleistocene are more like what we find in the fossil world compared with the rest of this. Okay, from the bottom of the Pleistocene all the way down, the fossils are all in water-deposited sediment. Water-deposited sediment. In the Pleistocene, that's not true. They're not in water-deposited sediment. They are in. It takes very unique conditions in the modern world to make any kind of fossil. One place is in the middle of Los Angeles, the La Brea tar pits. So for several thousand years, there's been this tar oozing up into pools. Animals go there. There's water on top. They try to get a drink. They get trapped. They get stuck in the tar, and they die and get preserved by the tar. And there are thousands of fossils there. In the Arctic, animals can fall into ice crevasses, like in Iceland, and get preserved. There's there's some very rare situations in a very dry desert where things just get dehydrated. And there have been a few human bodies that have fallen into acidic peat bogs in Europe, several thousand years ago. Okay, that's what happens in the Pleistocene, in the modern world. Only these very rare, unusual situations will make fossils. Below the Pleistocene, they're all in water-deposited sediments. Now, when I think of water-deposited sediments, I'm thinking of the flood. But so this gives us a unique insight into what it takes to make fossils. Conclusions. Well, live with unanswered questions. We don't have all the answers. But careful geological research finds this interesting evidence, increasing evidence against the geological timescale. Evidence that just doesn't fit that timescale. And the things that Dr. Phillips told you would be one of these. These fossils and rocks are another category. And to understand this, progress comes from taking the Bible as our guide, even in scientific research. There are abundant reasons to trust God's Word. We don't study geology to see if the Bible is true. The Bible gives us insights to understand the rocks and the fossils. The foundation. What foundation do we have? The Christian gospel is not about geology. But modern science claims to have proved the Bible is wrong. We are tired of seeing friends give up on the Bible and gospel because of this. And it happens too much. Our faith is on the Bible, not on science. But when we build on the foundation of faith, our science gives us better answers to scientific questions. And this is not my opinion. I showed you a list of all those scientific publications done by creationists. This works. There's an interesting thing about that I just want to point out. I read all the anti-creation material I can get. And when do I stop? Pardon? Okay. I read all this anti-creation stuff. And it's clear, these naturalistic scientists don't know how an educated creationist thinks. They just don't know, and they end up saying foolish things because of it. They only know their own views. They don't understand how worldview affects them. Okay, creationists, if I want to do science, I can't just ignore them. I have to know how they think. I have to know all their evidence. I have to know how they think and how I think. And then I can be all the time comparing those two and thinking how this works and how can I test between them. This is what my friends and I do all the time. So we have the opportunity to understand both views and compare them. They're not doing that. They're only looking at it from their own point of view, and I can give you many evidences for that. We understand their worldview and ours. So we haven't. They say that we are biased and have closed minds. No, I'm sorry. It's the opposite way. They only know their worldview. We know both. We're always comparing them. We have a distinct advantage because of that in science. We see things that we would not have seen if we hadn't been thinking that way. And the things that they're not seeing. Okay, evidence supporting long ages, primarily radiometric dating. But all these things I've talked about really say, no, it can't be right. Those long ages can't be right. Okay, I want to spend the last few minutes on another topic. The planners of this have these papers that we've written that they're going to publish, and along with that, there's going to be a 2-page item published called Origins Resources, and this is the first few lines of that to show you what it will look like. So why do we come here to talk? Just to entertain you? No, we want you to have materials you can use in your teaching and in your preaching. And this is a long list that we're giving you of very helpful resources, practical resources that you can use. And this is just the few lines of that. It gives you one website. This is the Geoscience Research Institute website. And that has a long list of books. This one by Art Chadwick and myself that you can download free anywhere on your phone or on your computer. And there are a lot of other things in this list. I'm going to show you one thing. I'll stop this, and then if you can bring up that video. Okay. A couple of years ago, I prepared 63 short videos. Each one, just a few minutes long, 3 to 5 minutes usually, sometimes longer, present an important concept out of that book, Faith, Reason, and Earth History. And they're useful for teachers. Dr. Phillips uses them in teaching her class. And one of our graduate students is busy right now translating them into Spanish. So it takes him a little bit to get this changed. But I'm going to show you one of these to give you an idea of what these are about. In this session, we're going to talk about how we came to have life. How did we go from a non-living universe to having life on this earth? There are basically two options. One, you can have creation of life by an intelligent inventor/creator. Or secondly, the predominant scientific theory is called abiogenesis, or chemical evolution. Life originated from non-living material with no intelligent assistance. Now, how would that happen? If you don't have a creator, how do you get life? Charles Darwin commented, perhaps in some warm pond, compounds could combine, and that's how life originated. In the left picture represents what you might have in a pond with mud and water and pebbles. On the right, you see a living cell, which is a fantastically complex thing. It's actually, if you could combine a lot of chemical factories, that would be a cell. So is that a realistic explanation of how life could begin? So if there's no creator or intelligent designer, the origin of life would require several things. One would require that the process could only occur by a long series of random, undirected, rambling biochemical reactions. Number two, such a process would not have any information about what its goals are or what to do next. Number three, each random event would have to be the correct one to connect up with any molecules already there. Number four, the process would have to invent, notice I said invent, the thousands of tiny molecular machines in a living cell. Number five, evolution was not involved. Evolution can only occur if there is a genetic system and a body, so natural selection can operate. In other words, you have to already have a living organism for evolution to function. Number six, to understand the significance of these several steps, compare this process to finding your way from Texas to Australia with no knowledge of geography, no boat or car, and you don't know what your goal is and you don't know what direction you need to go. There's another important issue here. If there's no creator or intelligent designer involved, the origin of life would require, number seven, exact random chemical reactions would have to occur. But the problem is that the rates of chemical synthesis are like this. Synthesis, making something, making a molecule, will go to the right, and the width of the arrow indicates how fast that works. But that same process can go both directions, and going the other way towards destruction will happen much faster. So how would you make something if it's going the wrong direction? Abiogenesis is how many scientists believe life began. Under the philosophy of methodological naturalism, abiogenesis is the only acceptable explanation for the origin of life. But is this scientifically realistic? So that's a sample. Maybe you can make use of some of those, and they will be available. There are other books available. Here's a little one that I've written, Creation, ? Really, ? It's a very readable book. It's written as a conversation between an atheist and a believer as they're on a geology field trip. So there are a lot of things that you could make practical use of in your teaching. So we hope that can be helpful.